Thank you.
All right. Good morning. Do you hear me? Great. So this talk is going to be a little bit different from what you heard so far, and I hope to entertain you today. First of all, I'm going to be speaking about the work of many, many people in this theoretical and computational collaboration, which is funded by NASA and the National Science Foundation in the US. We call it the TCON BBH DISC collaboration. It does have a number of graduate students on it, some of them sitting here in the audience and as well as postdocs. So I want you to see their faces so you can recognize them. And they are doing most of the work of, obviously, associated. Sorry? Oh, this is making noise. OK, but we can take it off. Yeah, thank you. Oops. OK. So if you see them around during the coffee break, please don't hesitate to approach them to ask them questions. So I couldn't not just start from this wonderful sketch of all the binary black holes that LIGO has detected. There are kind of nearly 100 so far. I would say 90 plus what's the official word. But with 04, we're really getting into really hundreds. And they really span really all over the mass spectrum, as you can see. So this is really amazing news today to have this. And last year, we heard about the news about PTAs, and hopefully what we have seen is really a huge background of supermassive black holes. At least that's what I hoped. Well, we heard about LISA. This is a LISA symposium meeting, so I won't be repeating all the great news that we have heard at this meeting here, and one of the advantages of being one of the talks in the last day is that I don't have a right to do that. But it's really exciting, and it's an exciting time, and an exciting time for me to be here to tell you about more on the theoretical aspects. So what do we expect in terms of supermassive black holes? Well, on the theoretical ground, we know that they should be there. They should be merging because they are consequences of merging of galaxies. Then that could get into the binary stage through a variety of processes. So of course there are a lot of processes, and especially when masses are comparable, these processes are thought to be very efficient at bringing the supermassive black holes into subparsec scales. Once they are there, they are very exciting sources for both LISA and PTA. But because these supermassive black holes reside in very gaseous environments, centers of galaxies, they should also emit electromagnetic radiation, and as well as jets. They should be actually very powerful in the electromagnetic spectrum. So one of the hope we have is to actually go after them and detect them electromagnetically. If we could do that, then these become really a very interesting potentially multi-messenger sources that can help us to localize events in the gravitational wave event, but also help us to study the astrophysical environment around these objects. So we heard today from Christy about the zoo of potential and binary systems, but also about dual system. And these are some of those, just a very few sample of those that I used to show in my slides. There is a variety of them, and it depends on whether you are going from 100 parsec or to few tens parsecs. So to parsec scales, the numbers drop down dramatically. And so there's a variety of potential signatures that one can look. There are periodic flares. There's direct imagings, of course, of double nuclei, sinusoidal-like curves, self-lensing we heard yesterday. And then there is also very exciting news about binaries potentially detected or in quasars lately. The good news is that while they are still very rare, with the new astronomical observatories, we should be able to uncover many binary GN in the future. Now, it's very difficult to really detect them electromagnetically, but if we know what signal to look for, perhaps there is a chance of it. Just to illustrate how difficult it is, let's remind that a few years ago when we predicted, with theoretical calculation, when relativity predicted the existence of gravitational wave recoil, the astronomical community went out there seeking for these objects. And they were looking really actively for a variety of sources, looking at double picometers of set galaxies, of set galactic nuclei, population of galaxies without supermassive black hole, et cetera, et cetera. There's always another interpretation. Okay, so it could be supermassive binary black hole. Hopefully, it could be something else. So I just put up this very interesting image here of an SDS image that was found by one of our students at RIT, which she called it extremely weird objects because the velocity shifts are extremely huge. So, well, what is it? We really don't know. And in order to really understand whether we really have in those type of signals supermassive binary black holes, we really need to do a good job at theoretical modeling, try to really understand what happened. So that's where I'm going to start, and I'm going to try to motivate now you or why we're doing what we're doing, trying to model this system. First of all, I just want to tell you this is a very challenging thing because, as you know, we need to span a very large, cover a very large range of dynamical scales. And so we can't definitely do that in just one simulation. All we can do is try to connect the dots among the various simulations at the different dynamical scales. Each of these dynamical scales will have to include the proper physics to describe the environments, and each of these simulations and models have their own challenge. But it's very important to be able to connect among these various models. Once you get to the stages where the binary reach the subparsec scale, then you can start modeling, taking the information from this previous simulation into your models. And, but even there, you have quite a bit of challenges because, first of all, you need to describe what is the environment close to the binary. So you might make assumptions about what kind of accretion disks might be there. And we really don't really know exactly what is the environment close to a binary black hole. So, I mean, the accretion disk around a binary black hole could be completely different from the accretion disk around single black holes. Typically, and additionally to that, well, there's a wider set of parameters that we have to use in describing these systems because, well, you have all the parameters that are typically people use to describe accretion physics around single black hole, plus all the extra parameters introduced by the binaries. In addition, if you really want to be in the gravitational wave-dominated regime, there is, as we're going to see, interesting physics that we need to add. Now, in general, what people do in my community is that we assume two different, reasonably say, different models. One is, and as a sketch, I asked Firefly to make me this sketch of these two potential models, and I think she did a good job if instructed properly. And so there's the first model, a gas cloud, which is describe a hot, radiatively inefficient system. And a second model, which is the circumbinary disk, a more cold, radiatively efficient model, which resembles a little bit more the single accretion disk situation. So most of my talk is going to focus on the second type of model, but I'm going to go over a little bit, also the other results. Okay. So a little bit more about to make you appreciate the challenge on this type of work is that in order to do a good job, you must include all the essential physics in the system. So what is it? Well, of course, gravity, right? So we have the Einstein's equation. MHD and magnetohydrodynamics, and that has to be accurate at the scale of the magnetorotation instability of turbulence, realistic thermodynamics, plasma physics, radiation transport. And in order to get, and these are the equations, right? So I'm not going to go all over these equations. Some of you might have seen them, of course, and but these equations are highly nonlinear. The system is highly coupled, and you have to have really very advanced numerical algorithm to make sure that you can resolve the physics and make the system run stably for long enough and give you really good physics out. So people have been trying to do that, and I'm going to walk you a little bit through just shortly here about what has been done. So we can start from the early work in 1D. So in that time, people were just evolving Newtonian systems in 1D, and what they found is that essentially the binary exerts a torque to a gas, and what happens is that it vacates the region close to the binary. So the news then was that nothing is going to happen. There's no electromagnetic radiation close to the binary because the torques will just push out all the matter, right? And so, well, gravitational wave interesting, but not electromagnetic radiation. This changed dramatically in the last decade, especially when people started to do models in 2D, then and then in 3D GRMHD. Now, a lot of the modeling today still focus on 2D, I must say, okay? So this is, of course, because these simulations are extremely challenging to do, and they are extremely long-term, so this is one of the reasons has focused on 2D. But lately, and there is this new papers by Duffel here, they have been comparing also a lot of the simulation that have been performed to date. And while they found that all the 2D simulations are pretty much in agreement among themselves, 3D gives some very interesting differences. So it's different in terms of how the circumbinary disk, by the way, CBD doesn't start for CBD oil, right? So it's just circumbinary disk here. So circumbinary disks are different. Mini disks different as well in around the black holes. And you can see here two pictures. The first one, they seem similar, right? But we're going to see the second picture has a third dimension. And that's where you start to appreciate what are really the differences between these two. But similar structure inside, close to the black hole, if you want. But the characteristics of the mini disk, the characteristic of the circumbinary disk are rather different. And then, as well as you can see there in this picture, so there are some differences. For example, in 3D, we see the existence of overdensities in the circumbinary disk, and we don't see that much in 2D. In 2D, we don't have spins, we don't have jets. We see that in 3D. And in 3D, you can do GRMHD. which is really cool. But one of the things that I think we all agree about 2D or 3D is that accretion seems to continue pretty much until close to merger. I'm going to see up to merger. And so that doesn't stop. Doesn't seem to be this idea that there is cavity, a huge cavity there forever. Actually, it's not. The cavity tends to fill, we're going to see. And in addition, there doesn't seem to be this idea that eventually the binary proceed and inspire so fast, leaving the disk behind. The decoupling seems to be really hard to find. So what about GMHD then? Okay, there's few numerical activity simulations have been done so far, and that's the reasons is that we have a huge range to explore, and these are very expensive simulations. But really, as I said, we are really interested to go after questions like dual jets, electromagnetic signature, especially the merger, and the signature of the post-merger, and so on. In order to answer this question, you must perform long-term MRI resolving relatively very efficient simulations in order to get answer to that. And we have done some of this simulation, which I'm going to show you in the next slides. So this simulation is extremely long, and this is a simulation of an accretion disk, which I don't know, at some point I will interrupt, because you see that in order to develop the MRI, it takes quite a long time until the disk develops turbulence and proceeds toward the in-spiral. In order to do these simulations, if we want to save computational time, we might use the post-Newtonian space-time description for the in-spiral regimes that helps us to drive the computational cost down. And so that is done typically with codes like, for example, Harm3D, here developed by Scott Noble, who's in the audience, and it does do a pretty good job at describing the stage of the in-spiral. And especially uses spherical coordinates, which is typically used in accretion disk physics community, because they are very good at describing angular momentum transport in the gas. So, as I say, this keeps going, so I'm going to have to interrupt it. But of course, we want to know what is in the cavity, actually, or what cavity close to the black holes. And in order to do that, this spherical code cannot handle the regions close to well. So what we do is that we use them to describe the circumbinary disk for hundreds of orbits, really hundreds, or hopefully one day close to thousands, and then pass it on to another code that uses Cartesian coordinates that can describe well the region surrounding the binary. And that allows us to do the simulation on its entirety up to the merger. Okay, we call this a handoff procedure. So we hand off a simulation data from one to another. How do you do this? You must wait that your accretion rate for the circumbinary disk reach that steady state. Okay, so quasi-steady state. Then you are in a situation where you're allowed to proceed and do this handoff. So what we found? We found that in general, during the phase of the circumbinary disk evolution, a generic lump or overdensity of material tends to form. And there are accreting streams departing from the circumbinary disk that falls into the black holes. The black holes form mini disks attract matter around them pretty quickly. These mini disks, as they orbit around, they collect material from the CBD, and as they get close, as one of the black holes get close to this overdensity, it gets filled more than the other one. So there is this process of filling and depleting material periodically as the binary orbit around this lump. Additionally, you can see that there is also quite a bit of interesting exchange between the two black holes. We call it sloshing. So there's really a very coupled system between the circumbinary, the black hole mini-disk, and the mini-disks themselves. One of the interesting lessons of 3D is that the mini-disks don't actually look alike at all, the simple models that people use. They actually have a very interesting 3D structure. We also found that if you try to do this simulation from large separations that are almost in the Newtonian regime, we do have very similar characteristics in terms of the appearance of this generic lump, as well as the accretion rate being pretty much similar. And so it tends to, accretion continues to fill the mini-disk. There's no decoupling, really. And I invite you, before the poster are taken out, to go to see the poster by Scott Noble about that. So, because we can do spins, we were very interested in exploring the effect of spins. And what we found was that whenever spins are present, the mass accumulated around the black holes are larger, depending on the direction of the spins. So the mini-disks are bigger, and I have to really get going, so my time is gone. And the outflows are 10 times stronger. I'm going to skip these slides here because my time is short, but we can calculate spectra these days, and we can calculate light curves. And you have, if you were here on Tuesday, you must have heard the talks of one of my PhD students, Kathleen Porter, about light curves. She has a beautiful paper out there. So I'm going to skip it. I'm going to go to show you some of the latest simulation that reached down merger. And hopefully this movie is going to play you. It's going to show first the simulation of the handoff of the circumbinary disk, and then a handoff to a Cartesian coordinate code. And finally, it's going to show you what happens inside the cavity. And you can see the extent of the domain here. On the white spot there, as far as the cavity has been excised for allowing us to simulate more efficiently in spherical coordinates the circumbinary disk. But at some point, we move this data to another code. And so this is, again, these are very long simulations. You can see the spherical coordinates here. And then we pass that on into a Cartesian code. And as soon as you allow the black holes to accrete mass, they do it. And they form these mini disks. Okay, so that happened really, really quickly. Okay, so because I have very little time, I want to show you just some of the 3D simulations that have been shown already by my PhD student, Lorenzo Enargi. And they go down to merger. And what you're going to see down to merger here is that some interesting dynamics happen. These, by the way, this is a simulation with spins that are aligned with the angular momentum. So you see the mini disk reaching down merger here. And watch very carefully what's happening close merger. If you can, also follow the movie on the polar sides, you can see that there is quite a bit of outflows coming out from the system. And as the binary gets down, you see that one of the mini-disks disappear and then the other disappear, but there is a lot of material falling down into the system, and then suddenly a lot of material again. So what exactly happened there, and my time is almost disappearing as well, is that we have this process where one of black hole mini-disks first disappear, then the other one, because the material of the circumbinary disk falls in, interact with the mini-disk. The mini-disks also have less space because the Hill sphere is smaller, and to exist. But a lot of, once they disappear, the jets associated with them disappear, as you can see here as well. But then soon later, after the merger, material gets down, refills the cavity, and the jet is reunited. So this is very exciting because it's a potential signature. Unfortunately, I do not have much time here to finish this, but there are specific frequencies associated with this type of dynamics that we can see. One is the lump frequency, and the other one is the bit frequency, we call it, which is the frequency of the binary as it passed through close to the lump. Again, so spin do matters. This process of mini-disk disappearance and mini-disk forming is really dominated very heavily by the direction of the spins. Okay, so as you can see in this case, one of the spins is down, there is no mini-disk formed. So in the interest of finishing up my simulation, again, masses are also important. They do have quite a bit of an effect on the size and shape of the mini-disk, mass ratio. If spins are not aligned, and I'm going to move forward because my time is slowing down. So here is my last movie I want to show you, because this is where the spins are not aligned. And there are very interesting effects associated with this, including the existence of potential kicks and merger. And you can see that the very interesting shapes of the mini-disk there. They really are not a traditional disk at all. And very interesting dynamics here. So I will conclude here, maybe get questions if you want to see more. You might approach me in the coffee break.
Thank you very much, Manuela. Any questions?
Yes.
Thanks for the very nice talk. Just to understand, because I also work on something similar, but more in spiral of the binary.
Sorry, could you repeat what you said?
Yeah, I was just saying that thanks for the nice talk, and I also work on something similar, but more on the spiral. And I was, just to be more greedy, what kind of physics do we also need to include in GRMSD to get even more closer to reality?
Yes, radiation is definitely, radiation transfer, I would say, is key. In our simulation, we do use a simple prescription radiation transfer. I didn't have time here to go through this, but it's really one of the key things beyond GRMHD, of course.
Okay, thank you.
Yes.
Yeah, thank you so much for a very nice talk. And so the question is the following. I mean, some of your simulations show the appearance of outflows and jets, and just in case you're looking at...
Where are you? Oh, sorry.
So yeah, some of your simulations show the appearance of outflows and jets, some others do not. And so the question is, do you have a sense what is the necessary condition for these outflows to form? It seems like spin and magnetization helps, but magnetization grows over time, right? So, I mean, so is there like a picture that emerges? When do they occur?
So jets are always there, even when the spins are not there, except that when the spins are there, they're way stronger. So in 3D GRMHD, we find jets, or you may call it outflows, in the case where, these jets are not that strong, but typically they're very, very powerful.
So MHD part is necessary.
Yes, yes, they're jets. This double, and then one, at least double closing. There was raised an interesting question what you would see far away. Yeah.
Just a quick comment and a question. So my students at Mesh just had a paper showing that the gaps aren't maintained by resonant torquing at all. They're maintained kinematically by epicyclic instability, so I don't think you'll see decoupling no matter what operations you start with.
I don't think there's decoupling.
And then my question is, so Zach Etienne has a numerical relativity code, black holes at home, and I think he's part of your group. I was just the whole filling of the cavity thing and handing off of codes. I wondered if you had any plans to try to like merge HARM 3D with, because black holes at home can do arbitrary coordinates on the.
Yes, we have discussed it. So thank you. This is pretty specific for those of us who work in this area. But yes, we do talks because he's part of the same collaboration about doing that. But right now, black hole at home is only handling vacuum space-time. So it's part of the future. We could do that. Yeah.
Thanks.
In the interest of time, let's thank Manuela and postpone questions for later.